T distributions versus F distributions. You remember a while back we compared T to Z, right? Well, now we're going to compare T to F because the F distributions are what gets analyzed when we are looking at ANOVAs or when we're conducting ANOVAs. So this T is referring to the distributions we look at with t-tests, and the F is for ANOVAs. Okay, so let's look at T scores, right, in a t-test and the T distribution. We'll look at this first, and then we'll look at what's going on here with the F distribution. So first of all, you will recall, hopefully, that there are an infinite number of T distributions, just like Z, right? There's an infinite number of, just like Z. Oh my gosh, that was a huge mistake. How many Z distributions are there when we are talking about the Z-score distribution? Well, only one, right? I can't believe that I made that mistake. See, everybody makes mistakes. Okay, there's only one Z distribution, but there are an infinite number of T distributions. Well, guess what? There are an infinite number of F distributions as well. All right, so let's go to the next property here. For T distributions, variance and standard deviation depend on the specific T distribution. Remember that if you're looking up, if you want to know areas under the curve, if you want to look up critical values, you need degrees of freedom to look at the table, and it's because the specific shape of the T distribution and how variable it is, whether it's leptokurtic or platykurtic, will depend on degrees of freedom. So that means that the variance and standard deviation are always changing, okay? So you need to look up degrees of freedom, use that in a table or in an app online, and then you can get areas under the curve and critical values. Well, the same is true for the F distributions, all right? It's not like Z. For the Z distribution, we learned that the mean is always 0 and the variance and standard deviation are always 1. Okay, but now we know that both for T distributions and F distributions, you can't say that the variance and standard deviation are always 1. It's going to change, and it's going to change depending on which specific distribution you're talking about. All right, so that's this property here. So the areas under the curve and therefore the critical values in hypothesis testing are going to depend on the specific T distribution. That's why we need a table. Same thing here. The areas under the curve depend on the specific F distribution. So that means that the critical values are going to depend on the specific F distribution as well. We need a table to tell us what those are. Okay, all T distributions, like Z, all T distributions are normally distributed. Well, where do you see the F distribution? These are not normally distributed. In fact, they are positively skewed. So do you remember the gun analogy, right? The little mnemonic I gave you with, the finger guns? If it's positively skewed, your finger is going to point where? To the positive end of the number line or the negative end of the number line? Towards the positive, right? I'm going to show you pictures in a minute, okay? So you can see what these distributions look like. All right, T can take on any value from negative to positive infinity, just like Z. But look at this. F can only take on a value from 0 to positive infinity. All right? In other words, F can never be negative. If you get a negative F value, you have screwed up somewhere. And we will look at why this is the case later as well. Okay, the mean for every T distribution is 0, just like it was for Z. Okay, so Z and T, the mean is 0. But the mean for every F distribution is going to be somewhere close to 1. All right, so again, it's going to depend on which F distribution. It's not, I can't say it's going to be 1 all the time. It's not, that wouldn't be true. Sometimes it's going to be a little less than 1, and sometimes it's going to be a little more than 1, but, it's going to be fairly close to 1. Okay, and then this last one, well, I've already mentioned it in the course of explaining this, but we'll cover it anyways. To look up areas in a t-table, you need to know the t-value that you've calculated, or that SPSS has calculated, and the degrees of freedom. Similarly, to look up areas in an f-table, you need to know the f value that you calculated, right, or SPSS calculated. That's your TS, remember, test statistic. This would be your test statistic value. You're also going to need to know 2 numbers for degrees of freedom, because one of them is for between groups and the other is for within groups. Now, this is something that you haven't learned yet. You've learned what between subjects means and within subjects, right? Whether you have the same people in every level or whether you have different people in every level who have not been paired or matched. All right, so you've learned about between subjects, but you haven't learned about between groups and within groups. So you're going to learn about that today. Okay, so the test statistic in all ANOVAs is F. Just like when we did the different t-tests, right? When we did the single sample and the independent t-test and the dependent t-test, our test statistic was a t value. Well, now when we do ANOVAs, the test statistic is always going to be an F value. Now, you've learned about F values before when we talked about Levene, right? Levene also calculates an F value. So both Levene's test and the ANOVAs calculate an F value. And here is what the different F distributions look like. Of course, I haven't plotted all of them because remember how many F distributions are there? An infinite number. So I obviously cannot, even if I wanted to, show you what they all of them look like. But I've shown you some representative examples here. So the numbers in parentheses refer to degrees of freedom. And remember I said that every F value is going to have 2 of these numbers, one for between groups and the other is for within groups. So you see that here. So this first one is for between groups. The second one is for within groups. Okay, the first one is for between groups. This one within groups. Between groups, within groups. So you can see that as we increase our degrees of freedom, here we did not increase the between groups very much. And that's because this number here, between groups, actually refers to the number of levels you have. Now, you might be saying, well, how can we have 2 levels? You just said that with a one-way ANOVA, we have to have 3 or more. All right, we can't just have 2 levels. But this number here is, I said it's the number of levels, but it's actually the number of levels minus 1. So if you saw 2 here, this actually means you did have 3 levels. Okay, so it's the number of levels minus 1. So this one would have 3 levels it was comparing. This one would have 4. This one would have 6. This second degrees of freedom here, that's within groups. And that's the degrees of freedom associated with your error term. And I won't go into detail how that's calculated, but I will say that this second number here is always going to be larger than the first one, right? So when you're reporting degrees of freedom, if you forget, oh, do I put between groups first or within groups? Just remember the larger one goes second. Okay, so from this, we can see that it's not on the x-axis here, but it would start at 0. Okay, you cannot have an f value that's negative. And some of them kind of look like, like it might have been normally distributed if we could have had negative f values, right? Right? If we could have, kind of looks like this would be normally distributed, but we can't. So there is a very definitive positive skew. And that's true for each of the ones that I have here. All right, so it starts off kind of looking like this. Few levels and a small degree of freedom for your error term. Kind of looks like that. And then as we increase the number of levels and increase degrees of freedom for our error term, we get something that is more traditional, I guess. Compared to what you've been seeing, this distribution would look more traditional. All right, so now it's time to learn about the F value and how analysis of variance can tell you anything about why means are different from each other, right? Did you have that kind of question in your head? Analysis of variance, shouldn't it be called analysis of means? Because that's what ANOVAs are trying to do, right? Just like t-tests, ANOVAs are trying to tell you which means are different from which. Like, which do we have a treatment effect? The ANOVA itself won't tell you where the treatment effect is. But if the ANOVA is significant, it means you have a difference somewhere among those means. How can that be if we're analyzing variances? Well, the answer is coming.